It's a great pleasure to have Francesco Maggi from UT Austin, who will talk about a mesoscale flatness criterion and its application to the exterior isoperimetry. Sorry.
Thank you, Stefania. So, and thanks to also to Connor and the organizers for inviting me to give this talk. So this is a joint work with Michael Novack, who is a postdoc at UT Austin. And we just finished the paper a few weeks ago. So we're pretty fresh on it. And the title is definitely a bit esoteric because I wouldn't know what is a mesoscale flatness criterion if I hadn't written this paper. So, so let me first of all maybe try to explain what we have in mind with this concept. So the story, as the title suggests, is related to the exterior isoperimetric problem, which I think at the end of the day will be an example of a geometric variational problem where these methods and ideas that we have found should be useful. So while studying the exterior isoperimetric problem, and I will explain why in a moment, we have found natural to formulate something that we call a flatness criterion, and which at variance with the flatness criteria that at least me and Michael were familiar with, first of all, does not operate at very small scales. So let me first of all quickly remind you of what people like me may describe as a flatness criterion operating at small scales. Okay, so the concept is essentially, for those who are familiar with it, it's essentially, I'm going to describe with this terminology, de Giorgi's or Allard's epsilon regularity theorems. Okay, but even without being familiar with GMT, the basic idea of this kind of result is extremely simple. Okay, the idea is the following: you have an hypersurface M inner n plus 1. It doesn't need to be in codimension 1, but let's say to fix ideas. Okay, so we have a nice hypersurface with bounded mean curvature. We use lambda as this bound on the mean curvature of our surface. So a lambda being a mean curvature, it has the dimension of an inverse length. Okay. So what does a flatness criterion tell you? It tells you that if you have a scale rho, a length scale, okay, at which is first of all small enough in terms of the inverse mean curvature. So this is, you don't even start if you're not small enough with respect to the bound you are given on the mean curvature. And second, you want that your surface, the area, n-dimensional area of your surface M in a ball of radius rho, of this scale rho, you look at its area, you compare it with the area of a disk. So of something that would be a completely flat surface inside a ball of radius rho, inside a ball of radius rho, an n-dimensional ball of radius rho, a completely flat surface as area omega n rho to the n. So you look at this scale invariant notion of local notion of area. If you're totally flat, this is 1, if you're a plane. Otherwise, you ask that it's small enough. Okay, it's smaller than some universal constant epsilon 0. Then under this only assumption, so that your area compares very favorably to the area of a disk at scale rho, and that this scale rho is not too large with respect to the mean curvature, under these only two assumptions, you discover that there exists an hyperplane such that your surface in a smaller ball, universal scaling radius, is a graph with respect to, say, the hyperplane with C1 norm that is as small as you wish. So if you want it less than a constant sigma, then you just have to take this epsilon 0 here, depending on n, lambda, and of course sigma. So this is essentially, it's telling you that there is an intrinsic scale for a surface at which it is a graph that you can somehow control. Okay, it's not obvious. Take lambda equals 0, take a catenoid, right? You can take catenoids and scale them until they become extremely flat. And you see, near the point of the neck of a catenoid, there is no graphicality, universal graphicality scale, because the surface is bending, right? The normal is using all possible directions in a very small, in arbitrarily small scales. So that's why this condition is so important, because it tells you a scale that is intrinsic to the surface where you can hope for graphicality, and then you get it. Okay, so this is what I understand as a small scale flatness criteria. I'm telling you, if the scale is small enough with respect to certain information, then we get graphicality with respect to a plane. Okay, so the criterion we have found is special in the sense that it's not a flatness criterion at small scales, it's not even a flatness criterion at large scales. So I think everyone here is familiar with Bernstein type theorems that tells you that if you solve a certain nonlinear PDE on Rn, then you are affine, right? It's like minimal surfaces equation on Rn, then you must be affine with some bounds on dimension, etc. So elaborations of Bernstein theorem essentially are what give you flatness criteria as the one I've just mentioned in the local case, okay? So there are theorems like that out there, and our theorem is not exactly, our flatness criterion is not even that, okay? Our theorem will be, as the title suggests, a mesoscale flatness criterion. So mesoscale means intermediate scale, okay? The scale at which our theorem will operate will be in between a lower bound and an upper bound, as we will see later on, and it will give you an intrinsic scale to the surface at which you have flatness. By flatness, I mean graphicality with small c1 norm. Okay, so this tool, this mesoscale flatness criterion, is what is the crucial tool in resolving the exterior isoperimetric problem, which is the main result about isoperimetry I will present. And also, we expect that this kind of tool will have other applications. Okay, so it's because it seems a natural tool in every situation where you have surfaces that inside the compact set, they have a complicated geometry. So you cannot expect that inside this compact set, they're just graphs, okay? At infinity, they will also have a complicated geometry simply because maybe they cannot decay to an hyperplane. Their curvature is positive, so they cannot decay to anything nice. They have to close up themselves, say. But still, it could be crucial to understand their flatness at a mesoscale in between where they have this non-trivial topology and in between they have these general bounds on their spatial dimensions, okay? So maybe this is very vague, I don't know. So I decided to try to open the talk with these kind of general ideas, okay? So now the talk is about somehow giving substance, okay, to these claims and explaining in more detail what I really have in mind. Okay, so let's start with the exterior isoperimetric problem. So this is a classical variational problem. In our case, we consider W, the obstacle. It's a compact set. V will be our volume constraint. And then psi W of V will be the exterior isoperimetric problem with obstacle W. So essentially, W is the region of space where our droplet E is not allowed to sit into, okay? So droplets will be confined into the complement of the compact obstacle W, okay? So I'm denoting this region of access for the droplets as omega. So please keep in mind the omega and the W, okay? Because these are the two pieces of notation we will need. And so what it's minimized is at fixed volume, fixing the volume of the droplet V, you minimize the perimeter of the droplet inside the complement of W, inside omega. So in this picture, you see, for example, my droplet will have this area is something I'm trying to minimize, not this part of the boundary of my droplet. That's free, okay? Somehow, the part of boundary that you have in common with the obstacle, it's for free, okay? So for example, if you have obstacles like this, it could be a good idea, right? To put two pieces of boundary somewhere here to enclose a large volume by paying a little area, right? So for example, if you have an obstacle that has a lot of different pieces, it could very well be that locally the best behavior is kind of connecting these pieces with kind of walls, okay? Like this one. Okay, so this is the exterior isoperimetric. It's exterior because rather than being inside the container, okay, I am outside an obstacle. Okay, once you have the exterior isoperimetric problem, what are the basics? Okay, you always have minimizers for every volume. These minimizers have constant mean curvature. So what is constant mean curvature? The part of these minimizers, the boundary of these minimizers that is inside omega, the exterior of the obstacle. That part is constant mean curvature. Okay, so going back to this picture, this part is constant mean curvature. This part of the boundary is constant mean curvature. Of course, the part of the boundary that is in common with the obstacle will have the mean curvature of the obstacle. Okay, you have no condition. So that part is constant mean curvature, which is actually, by the way, equal to the derivative of the relative isoperimetric function of the exterior of W for almost every V. That's not so important for the talk, but just to mention the basics. And you have Young's law. So if whenever the boundary of the obstacle is decent, I mean, say C11 is regular enough, the outer unit normal to the droplet EV is orthogonal to the outer unit normal to the obstacle. Okay, you have this 90-degree law known as Young's law. Okay, these are the basics. Examples. For example, when you have a V small, when you work at small volume, these minimizers will look like half balls. So they will look like half balls of the volume V. Their mean curvature will be extremely large because they will be tiny droplets, right? And they will you will see just a droplet essentially sitting at the point of lowest curvature of W. Okay, so that's the most convenient position where to place this droplet. And that's the behavior at V small. Conversely, another behavior that you easily guess is the behavior for V large. So for V large, you imagine these extremely, the volume of the region enclosing that you want to consider is big. Big means much bigger than this length scale of your obstacle W. So what you expect to see? The obstacle should be a sort of perturbation of the Euclidean isoperimetric problem. So you expect minimizers for large volume to be very close to balls of volume V. Okay, with the obstacle acting as a tiny perturbation. In this case, the mean curvature of these minimizers is also again order of the volume to the -1/n+1. So in particular, the mean curvature is going to 0 as V goes to infinity. Okay, so like the mean curvature of an extremely large ball, larger and larger balls, smaller and smaller mean curvature. So our focus here will be indeed into the problem of understanding what can be said about this exterior isoperimetric problem in the large volume regime. So the question, to be honest with you, I mean, the first time I look at it, I said, okay, this is trivial because they will look like balls, and then I'm going to apply quantitative isoperimetry and I will get everything there is to know about them, okay? So let me explain you why I was too optimistic. So a closer look to the volume going to infinity regime. So if EV is a minimizer for the exterior isoperimetric problem with obstacle W, then we expect EV to be close to a ball of volume V. So B stands for ball, and this upper script V for the volume of the ball we are considering, with mean curvature going to 0. You can say more, of course, because first of all, by isoperimetry, the perimeter of the minimizer EV is just larger than the perimeter of a ball of volume V, since just it has volume V, right? So that's the first bound. The other bound you can have is just a bound with competitors. So I am a minimizer here. I can compare EV with any ball centered at X with volume. Okay, I cannot really say V. I should probably have said some W here because I want that the ball of volume W centered at X intersected with omega must have volume V. So I can do this kind of comparison. Essentially, the kind of comparison I have in mind, if this is the obstacle W, okay, I try to place a ball somewhere so that centered at some point X, so that the volume enclosed by this ball minus W, okay, is exactly V. And by optimizing a bit with this construction, you easily prove that the optimal value in the exterior isoperimetric problems of psi W or V over the perimeter of a ball of volume V. So this ratio goes to 1 as V goes to infinity. So that's the first information you have. What is the asymptotic behavior of the energy? The energy, as expected, behaves exactly as the energy of balls, the perimeter of balls of volume V. Okay. The second thing you want to do, okay, you say you have just used Euclidean isoperimetry, so why don't you want to use a quantitative Euclidean isoperimetry? So this is a theorem with Fusco and Fratelli, where we prove that not only the perimeter of V is larger than the perimeter of the ball of volume V, so this quantity is larger than 1, so this quantity is non-negative, but actually this quantity directly controls the distance of E from a ball of volume V centered at some point X, renormalized by the total volume. So essentially, you're saying that the size of perimeter of E over perimeter of BV minus 1 controls the volume of the symmetric difference of the best ball approximating E in volume. Okay, since you see here we are saying something very close to say that this goes to 0. Okay, this psi W of V is not exactly the perimeter of EV. It's the perimeter of EV relative to omega. Okay, so if I want the total perimeter of EV, I have also the part of so if I want the total, if this is a minimizer, right, the total perimeter of EV will also count this common boundary. I should also consider that. Okay, you consider that, there is a little error, you apply quantitative isoperimetry, and you discover that a minimizer EV, you can find the center X so that your minimizer EV has normalized distance in volume, normalized by V, which is going to 0 with a quantitative rate. Okay, nice. So you even can say not only that in energy you're close to a ball, you can always say that you converge. Once you can say that you converge to a ball in L1, you can apply what I call flatness criteria. Okay, you can apply regularity theory together with the information that this curvature stays bounded, and you can discover that actually you converge to this ball in a much stronger sense. Not only the volume of the symmetric difference goes to 0, but actually you find that the boundary of your minimizer is a C1 small graph over the boundary, over the sphere bounding the ball BVX. Okay, well, not exactly that. So it's not true that the totality of the boundary of your minimizer is a graph over the totality of a sphere. It's weaker than that. So where it's weaker is in the fact that you can actually say that the boundary of EV is a C1 graph over a part of the sphere, but only at a distance which goes like R0V, V to the 1 over n plus 1. What is this quantity? So this R0V is, R0 is actually something that goes to 0. So this is small with respect to the V to the 1 over n plus 1, but still the product of the two goes to infinity. Okay, so it's like outside an extremely large ball, extremely large with respect to the size of the obstacle, which is order 1, you know that you are a spherical graph against a sphere. Okay, but it's a bit annoying because you just know this, okay, at a scale, outside of a scale, that is actually incommensurable with respect to the obstacle itself. So the drawback of all these nice analyses you can do with quantitative isoperimetry is that there is absolutely no information that is specific to the obstacle we are looking at. In other words, if I think that exterior isoperimetric problem with D large, everything looks like a ball, it's true at first order, but the point is that when you say that, you have absolutely no idea how to distinguish two different obstacles, say W1 and W2, okay? They are all the same from the point of view of exterior of applying isoperimetry, quantitative isoperimetry, and flatness criteria, local flatness criteria. They're exactly the same. Every obstacle is the same, okay? As soon as they are, say, same diameter, there is no way here to distinguish one from the other. Okay, so this is a picture trying to convey the situation, okay, what I've just described. Essentially, this is my obstacle, and I actually have discovered that, yes, minimizers will look like gigantic balls, but the problem is that they look like gigantic balls outside of this green spherical region, and the radius of this region goes to infinity. So the radius of this region is essentially incredibly large with respect to the obstacle. So if I look at this problem from the point of view of understanding what happens at scale of order 1, okay, or even at very large scale, because this is going to infinity anyway, right? So I mean, it's not going to a constant, okay? I have absolutely no information. So the question that we started from is, can one say something general and related to the obstacle about this problem, okay? And what are the tools that one needs to do that? Okay, there is a first idea that it's obvious, okay? The first thing you try to do, okay. You say, okay, I've been studying these minimizers EV from the point of view of the quantitative isoperimetric inequality to discover that they're both. But there is a much simpler point of view that I could have used. I could have just said, okay, let me fix a good old compact set K, okay, containing my obstacle, and then these minimizers will have area estimates inside these compact sets. So just because they're minimizers, and therefore they have an L1 lock limit, subsequential limits, right, in L1 lock. So what are the limits that we see when we do that, and what are their properties? So, and this brings me to the topic of isoperimetric residues. That is a concept we introduced to describe what we observe here. So, as said, the idea to say a bit more is start looking at L1 lock subsequential limits of minimizers EVJ in this problem as Vj goes to infinity. Okay, these L1 lock subsequential limits, they exist just because of standard compactness, okay? So let's call F one of these limits. So by L1 lock limit, I mean that if I took the symmetric difference between EVJ and this set F, inside a fixed ball, the symmetric difference goes to 0, okay? Okay, first thing we can say is that, recall that we said before, right, the mean curvature of these minimizers of large volume must be going to 0. So if this is correct, as it is, we expect that this L1 limit, L1 lock limit, will have 0 mean curvature. So there will be minimal boundaries. So sets that are bounded by a minimal surface, okay? That's the first information. So what we expect to see is that when we look at things at on a compact set, the L1 lock limit are sets which are bounded by minimal surfaces, okay? Okay, nice. These will be minimal surfaces, however, not entire minimal surface, not complete minimal surfaces, because these minimal surfaces will have boundary themselves over the obstacle, okay? So there will be non-trivial, even in low dimension, there will be non-trivial minimal surfaces. Okay, this is nice, but to say more, to understand what's really going on, we cannot just be happy in transferring the information on the mean curvature, okay? We need to transfer the information that the EVs are minimizers in a variational problem. So we want to find what is the variational characterization of these limit sets F. They must themselves be solving some sort of variational problem because they come as limits of objects that solve a variational problem, okay? So, and this is where this topic of isoperimetric residues comes into play, okay? So let me try to explain what me and Michael mean by isoperimetric residue of our obstacle W. So I need to introduce this class F. So this will be sets F and normals nu. So nu will be a unit direction in plane in Rn+1. So we want sets with the property that the projection of the boundary of F over the orthogonal to nu to nu is the orthogonal to nu. So we need sets that once I fix the direction and I look at nu perpendicular, okay, I want the boundary of my set to have full projection on nu perpendicular, first property. And second property, I want the boundary of my set, so I'm correcting some mistakes in my slides as we go. The boundary of my set, I want it to be contained in between a slab associated to this normal nu. So I consider the class of sets, okay, was boundaries, subsets of Rn, was boundaries contained in a slab around this direction nu, and was boundary as full projection over nu perpendicular, over the hyperplane orthogonal to this nu. So there are no holes, okay? Good. So take a set of this one. Of course, what is the obvious example of such a set? A half space with normal nu, okay? This will be the basic example of such an object, okay? But notice that if I take a half space, I have only one choice of nu, right? Because if I take the horizontal half space, I cannot take nu to be something slightly tilted, because otherwise this second condition does not hold. So actually F and nu are very tightly related here, okay? Once you have F, you have only one nu that you can use. So, okay, given this family, so let me fix my slides here, I missed this point. So we define the residual perimeter of a pair F nu with respect to W as follows. So let's do the following. We look at our set F, right, which has full projection over nu perpendicular, and now we look at how much perimeter it puts inside an infinite cylinder with axis along the direction nu and horizontal radius r, okay? So we look at the perimeter of our set F inside this cylinder, which is as infinite height, but as laterally as radius r, outside of the obstacle. So in this picture, the area of the boundary of F that we care about is not everything, it's just this part here, okay? So the part here inside W is for free, we don't pay it. Okay, and then we compare the total area here, we compare it with omega n r to the n. So we compare it with the area of the cross section of the cylinder. Okay, in general, we expect this quantity to be non-negative. Actually, it's true, it's non-negative because of this projection conditions and the divergence here. Okay, so you see, the smaller, so in a sense, the more my set is good at minimizing perimeter, the larger this quantity is, right? So, and this is the quantity that we are going to minimize. Of course, I cannot just minimize, you know, I cannot write infinity minus the total perimeter here on the infinite cylinder. So what I have to do this for every radius and then send the radius r to infinity. Okay, this should capture the residual perimeter of F, given that it can save crossing the obstacle. That's the idea. So, and then you look at the set that has the largest residual perimeter. Seems strange, why the largest? Well, because the largest residual perimeter means that the perimeter of F is as small as it can. Okay, so that's why it's related to minimal. So the isoperimetric residue of the obstacle W is found by optimizing the residual perimeter, okay, of this pair F. Optimizing means taking the supremum, okay, because this means that F has a small perimeter as we can get. Okay, so if you think a moment about it, this is a plateau problem with free boundary on the obstacle and at infinity. So because the obstacle, because of course we are saving crossing the obstacle, so definitely we want to have a 90-degree condition when crossing the obstacle, right? And also with a sort of free boundary at infinity, because in our competition class, apart from the fact that we must be trapped between parallel hyperplanes, we are free to go to infinity, right, inside this slab. So there is a sort of free boundary at infinity and a free boundary over the obstacle. Both free boundary mechanisms are active here, okay? So that's what this isoperimetric residue captures. I will say much more about this quantity R of W, okay? In terms of understanding geometrically what it means exactly. But for the moment, let me just say that it scales like an area. So if you do R, if you do R of lambda W, this goes like lambda to the n R of W. So it scales like an area. So it's not wrong of thinking about it like some sort of n-dimensional area associated to W. And that's what I was just going to say at the end of the slide. So it's close to a sort of sectional area of W, but it's not quite that. It really depends on the fine behavior of minimal surfaces with free boundary over the obstacle. Okay, what are we going to do with these isoperimetric residues? Why they are important? So first of all, they're useful because they give you something that is not obvious. So we know that this guy over this guy goes to 1. The ratio goes to 1. But this, of course, doesn't mean that if you do psi W of V minus this perimeter, the difference has a limit. Okay? First of all. So it's not obvious that the difference between the optimal perimeter and the perimeter of a ball of radius V has a limit, first of all, in general for an arbitrary obstacle. And also that this limit can be characterized by some geometric problem, but that's true. So what is true is that the isoperimetric residue, and that's why we have chosen the terminology, is because there is the first residual presence of the obstacle in the energy expansion of the exterior isoperimetric problem. So that's why we have called it isoperimetric residue, because it's, in a sense, it's what is left of the obstacle when you send V to infinity, okay? Of course, I mean, this is a sort of Taylor expansion. This is huge with respect to RW. RW is a constant, so this is really much smaller than this thing. At the same time, perimeter of BB, it's not interesting because it says nothing about the obstacle, right? So that's why I want to look at the next order, because it doesn't contain much information about the obstacle anyway. So then second property, there exists a radius, a critical radius, depending on the dimension of the obstacle, and there exists a maximizer F of this isoperimetric residue, such that fix your favorite radius R,
and outside of this ball of radius R2, the boundary of your favorite minimizer of volume V is going to be a C1 small graph over this maximizer in the isoperimetric residue problem. So as a matter of fact, as much as balls were giving us a resolution model for the boundary of a minimizer far away, these maximizers in the isoperimetric residue problem give us a model for minimizers at any finite scale. So you fix a scale R, and then on the exterior of a ball of radius R2 universal, you find one of these maximizers F in the isoperimetric residual problem, and you are a graph above them. Okay, I will give you a picture in a moment of what this geometrically means, so that it's easier to follow my argument. But let me just, first of all, say that the proof of these results is quite non-trivial, and it actually requires a delicate blowdown and decay analysis for exterior minimal surfaces, which in my terminology of my very first slide would be what I've called an exterior flatness criteria. Okay, so this result is already quite delicate to prove and involves not just the local flatness theory that I have applied to get the graphicality over the sphere. This really uses these blowdown related exterior flatness criteria that are vaguely related to Bernstein theorem, quantitative version of Bernstein essentially. Okay, so that's the picture I promised you. So this is the picture that shows you that even with all this work, so even with the quantitative isoperimetric inequality and the blowdown results for exterior minimal surfaces and the very fine decay of these exterior minimal surfaces that you need, because it's not just they go to an hyperplane. You need very precise decays given in a paper by Schoen using a fine PD arguments. So even with all these tools, you're not done yet, okay? Because if you look at what you've just said, this is the picture that you have in front of you. So say that this is our obstacle W. So what we have learned is that outside a gigantic ball of radius R0 V to the n plus 1, we look like a small graph over a sphere. Then we have discovered that whatever R we fixed, we can choose a very large number. This thing is going to infinity, so eventually it will be incredibly larger. Outside of a universal radius R2, our maximizers in the residual problem will be very flat, and the boundary of EV will be very flat against it, against this against this maximizer of the isoperimetric residue of W. So we have a good model, a very flat model inside some annulus, R2 universal up to your favorite R. We have another good model, the sphere, outside of this very large radius. And then we have a mesoscale region, okay, in between, where we don't have anything. So, and this is a bit unfortunate because actually the blowdown analysis I was mentioning tell you that this boundary of F stays nice and flat forever, okay? So the maximizers in this relative, in this isoperimetric residual problem, outside of a universal scale, they will be super nice, planar-like minimal surfaces, decaying like a fundamental solution of the Laplacian to this hyperplane in the nicest possible way. So it would be tempting to say that, okay, you know what? In the mesoscale region, the boundary of EV must still be a graph with respect to this object, and then do a nice transition to the sphere I want to attach to it. But as a matter of fact, you have no idea about that. So there is nothing at this point that tells you, for example, that these set F, this local limit F is like asymptotic to this plane, and this ball up here is asymptotic to a tilted plane, okay? Or something that has a non-trivial distance. So you don't know these things, okay? It can be really, in a sense, it can be really disappointing from this point of view. Of course, I mean, here I'm saying that these maximizers in the residual isoperimetric problem are very flat. That's true. Inside this ball of radius R2, they will be extremely complicated. It depends on what is W, okay? If you imagine that W is a collection of connected components, you can easily imagine that these sets F will attach these different connected components with little pieces. It's not even clear that the boundary of F is connected, okay, outside of these, actually in general, clearly false, outside of this ball BR2, okay? The behavior becomes nice after a scale 1. Of course, again, the Allard, the Georgi flatness criterion, the local version will tell you that, okay, here F will be complicated, but actually the boundary of V will be a graph over this boundary of F up to the obstacle, okay? So it's really that here I'm isolating this scale R2 because it's the scale after which the boundary of F is very flat. But actually, even from 0 to R2, everything is absolutely nice thanks to the local flatness criteria, okay? And we can say that this set F is a perfectly nice model for the boundary of EV up to the obstacle, okay? So that's why this isoperimetric residual problem is so cool, because it really tells you everything on a scale of order 1. But unfortunately, as said, it's like we have this hole. It's not like we have this hole. And now the question is, what are we going to do to understand minimizers in this mesoscale region? Okay. Okay, so this is the point where we use these so-called mesoscale flatness criterion. So whatever the mesoscale flatness criterion is, I will come to that in a moment, it will tell you this. It will tell you that there exists a radius, R1. So far I have introduced 3 critical quantities, R0, that is this thing going to 0 as V goes to infinity, but still such that R0V, V to the 1 over n plus 1 goes to infinity. That is the radius outside of which the sphere is a good model. Then there is R2, the radius such that outside of this radius, every minimizer F in the isoperimetric residue is very flat. And I am discovering a radius R1 such that between R2 and R1 times V to the 1 over n plus 1, the boundary of every minimizer is a C1 small graph over the boundary of F. So this is nice because you see R1 V to the 1 over n plus 1 eventually will be larger than R0V, V to the 1 over n plus 1, because this R0 is going to 0, always, okay? So at a certain point, R0V will be smaller than this R1 we have been able to put here. And then, in a sense, you see, this mesoscale flatness criterion allow us to propagate the information of graphicality over the boundary of F from a scale that is maybe large but fixed and independent of V, to a scale that is natural to the problem because it's R1 V to the 1 over n plus 1. And eventually the scale of propagation will be larger than the scale outside of which we are close to a sphere. So the two scales will overlap. Okay, there will be an overlapping between the 2 resolution models. And we end up with this nice picture. We end up with a nice picture where we can characterize the boundary of EV as a C1's normal graph outside of this ball in terms of the sphere, inside of this ball, full ball now, in terms as a graph over the boundary of the maximizer in the residual isoperimetric problem. So theorem 1, if W is compact, then we have the energy expansion in terms of the isoperimetric residue, and we have a full resolution of exterior isoperimetric sets up to the obstacle itself, okay? Full resolution, I mean that the term resolution is used, right, in, for example, in PDE theory when you have a model, solution, and ansatz, and you show that you are, say, a C1 perturbation of that ansatz. So here it's what I'm trying to say here. So I'm saying that I have fully resolved the exterior isoperimetric problem in the sense that it's not that I cannot fully resolve it with just one model, okay? I need the sphere for modeling what happens at very large scales, and then I need maximizers in the isoperimetric residue problem to model whatever happens between the obstacle and a scale that goes like constant times the volume to the 1 over n plus 1. But given these 2 objects, it's completely modeled as a C1 small graph over them, okay, with the C1 norm that goes to 0 as V goes to infinity, okay? So we obtain the full resolution of this exterior isoperimetric problem. In particular, we discover a topological property. So this is why I think these kind of theorems are interesting, because they also give you topological properties that are true, even if I can't characterize this boundary of F explicitly, right, for an obstacle. But just the fact that it is flat, it's a graph or an hyperplane outside of this ball R2, tells us that the boundary of EV minus the ball R2 is an n-dimensional disk. So the topological information that essentially outside the scale of order 1, the boundary of these minimizers will have the topology of a disk, which is perfectly natural and expected, but is not trivial to prove. Okay, so because you need something like the thing we had said, because you see, if I cannot say what happens in the mesoscale region, right, I don't know if there is topology in the mesoscale region, right? So that's why this theorem gives you this property of being an n-dimensional disk all the way up to order 1. And you cannot do anything better, because at a certain point, below a certain scalar 2, the boundary of F will start having a topology, because maybe the obstacle forces it to have a topology. And then you cannot hope this information to be propagated farther near the obstacle. But it's quite, so it's a sharp result. I mean, you cannot say anything better, okay? Okay, before I go back to the mesoscale criterion, I have a quick slide about these isoperimetric residues. So what are the basic properties one can keep in mind? So first of all, I mentioned that it behaves like an n-dimensional area just by scaling, right? But it's in a sense much more than that. So it's trapped in between the largest hyperplane section of the obstacle. So if you pick the hyperplane, which puts more area inside the obstacle, okay? This gives you a lower bound on the isoperimetric residue. From above, you take the obstacle, you pick the direction over which the obstacle has larger shade, has larger projection, shadow, sorry. The two numbers are in general different. Maybe for some sets they are the same. In general, they are different, slightly different, right? In most cases, they can be quite far. Of course, if you start having sets with strange behavior. And the isoperimetric residue is somewhere in between both of them, okay? So in particular, for example, very trivial remark from this, whenever W has positive volume, right, the S of W, the measure of the hyperplane section, is positive, and so the isoperimetric residue is non-trivial. Actually, you may wonder, okay, but wait a moment. I mean, you proved these expansion formula, right? It's a bit a boring one if R of W is equal to 0, because you're saying nothing when R of W is equal to 0, right? It's just that the difference goes to 0. It's more than the ratio, but it's just the difference goes to 0. So when it is true that R of W is non-trivial. And actually, this is extremely general. So the next general fact about isoperimetric residues, R of W is 0, essentially if and only if the obstacle is purely Hn unrectifiable. So what this means is that you need to find a compact obstacle. So everything we prove just holds for generic compact obstacles, okay? But if you want to know when is that R of W is non-trivial, when it's positive, well, the bad case where it's 0 means that W is unrectifiable, which means that W has a 0 area intersection with every n-dimensional surface. So you take any n-dimensional rectifiable set, you compute the intersection of its area with W, and you find it 0, okay? So, I mean, of course, I mean, this means that you need pretty pathological obstacles, okay? Of course, with very little physical meaning to get a trivial isoperimetric residue. So in extreme generality, this theory is already non-trivial. I mean, it's R of W is positive. You can also have fun and try to optimize R of W. For example, you can optimize R of W under a diameter constraint. So if you just optimize R of W under a volume constraint, you say compact set with volume 1, you can send R of W to 0. You see it easily from property 1. But if you fix the diameter of your sets, then you can see that R of W is maximized by balls. And actually, there is also a characterization of the equality cases that of this inequality that we give, which, I mean, it's a characterization. So. But it's delicate. So it's not true. You don't have a rigidity theorem like balls are the only maximizers of this isoperimetric residue. Okay, it's a bit more complicated than that. So I will leave this for people interested in opening the paper. And then property 4, as I was mentioning, there exists a radius such that if you get a maximizer of the isoperimetric residue, then the boundary of F is a graph over the plane new perpendicular of a solution of the minimal surface equation, and this function is constant if we are in the planar case. Otherwise, what you get is a very precise set of decay estimates. So essentially, you decay to a constant like the fundamental solution of the Laplacian. Okay. So this is and this is non-trivial, right? Because imagine, for example, in the plane where you could have a catenoidal neck. So alpha catenoid, right, could be an example of something growing logarithmically. Okay, that could be a perfectly legitimate exterior minimal surface. Of course, it wouldn't be a competitor for the class of RW. So when actually you prove these theorems, it's quite important to get to the point where you exclude this kind of objects. So let me a moment. Okay, so okay, now the mesoscale criterion. So I think I still have a few minutes, like 5 minutes maybe.
Yeah, 5 minutes is
Okay.
totally fine.
Okay, so just to give you a statement, so it's just one slide essentially, it's left. Okay, so what is the statement now of this mesoscale flatness criterion? So we work in the class of hypersurfaces that have mean curvature bounded by lambda and have boundary actually. So these will be surfaces with boundary. The boundary will be contained in a sphere of radius r. So the kind of situation we have in mind is surfaces with bounded mean curvature, which have a non-trivial geometry inside of a ball of radius r, and have mean curvature bounded by lambda. So, but we look at them just between scale r and scale 1 over lambda. Okay, so 1 over lambda, because that's anyway what is reasonable given having in mind the Giorgi or Allard's theorem. You cannot work with this kind of surfaces with scales that are comparable to 1 over lambda or even bigger than. Okay, so it's completely pointless. And then essentially you say, okay, say that here locally I may have some topology, holes and stuff. Okay, you forget about that. You just cut your surface over the sphere and you look at its boundary over the sphere. Okay, and then you just take what is left. So we just take this part M. Okay. Okay. Remember the Giorgi's theorem, right? So the Giorgi's theorem, he had this notion of area in a ball divided by the area of the n-dimensional disk, and that needed to be close to 1. So that's what is called in the jargon of these theorems a flatness control parameter, let's say. Okay, so here we will need 2 of them. We will need something called we call the angular flatness and something else called the area deficit. So what are these 2 flatness parameters? So the first one, the angular flatness, is obtained as follows. So you have your surface. It's natural to consider our surface on annuli, right? Because it has a hole. It has a hole here in minus BR. So we consider it at a scale S between the ball BS and the ball B2S in an annular region. In this annular region, we look at the distance squared of a point y over our surface. We do y over modulus of y, and we take the distance from an hyperplane through the origin intersected the sphere. So essentially, I am considering, given an hyperplane, h to the origin, I am considering the cone, a cone of opening epsilon around this hyperplane, and then I am slice by slice of my surface. I am measuring the angular deviation. So, but I'm doing this in an integral sense. Okay, so it's true that my surface is not contained in a small cone around this plane. It could have some parts that exit, but they have small total area. So this L2 flatness is globally small. Okay, after you integrate. So this is the first flatness criterion. And notice that it's specific to a given hyperplane H. So you have that hyperplane, okay? So the second quantity that we are going to look at, it's very similar to the Giorgi's or Allard quantity, okay? So the Giorgi had the area of M inside the ball of radius R divided by R to the N. Now we cannot really have that because we have the hole, remember? So I have to take out definitely the hole, and I have to work with radii R larger than the size of the hole, okay? Okay, this quantity is not monotone, okay? It's not the right quantity, okay? If because of the hole. Also, there is the aspect of the mean curvature. Remember that the Giorgi had this lambda times R very small. Okay, that's also here represented by, you look at your quantity at scale R, and you look at every scale row between the hole and the R you're working at, and you weight it with lambda. Okay, these, when R is equal to 0, classical fact, crucial in Allard's theory, this quantity is monotone increasing, okay? And it's constantly equal to omega n if you are a plane. Very nice. Okay, however, we have the hole, so it doesn't work like that here yet. So we need another term, which is this term here. So this is a term in this quantity that it's concentrated on the boundary of the hole. So there is the conormal of my surface with boundary there. And this term here is crucial, right? Because to get a monotonicity, a monotone quantity. So this quantity where you have what you would have in the George's theorem, but with the hole. Then you have the correction because the mean curvature is not 0. And then you have a correction because there is a boundary term when you try to prove the monotonicity formula. So if you cook it up like that, you get a quantity that is increasing as the radius R moves from the radius of the hole to 1 over lambda. Okay, so that's nice. Even better, if this quantity theta is constant on some interval of radii R1 and R2, then M in the respective annulus, it's a cone. So that's a crucial property, right, of these monotone quantities, that you can understand the constancy case and you can characterize it in terms of some homogeneity property. So that's what happens here. We get homogeneity, we are a cone, if this is constant. What is the constant that corresponds to hyperplanes, so to flat objects? The constant is omega n. So we look at the end that this delta, our delta will be the monotone quantity increasing, the negative of it, and then omega n. So we measure, in terms of this monotone quantity, how far we are from being hyperplanes. Let me notice this. Checking that this quantity here is constant on an hyperplane, okay, requires a cancellation that happens because of the boundary term, okay? So the boundary term here is, there is a cancellation that happens with the omega n, but the omega n alone cannot account for the whole, okay? So to compensate, because I'm not dividing here by, what would that be? R to the n minus capital R to the n, okay? So there is really a non-trivial algebraic fact related to this term that tells you, that gives you the right computation on hyperplane. Okay, so this quantity is what you call the area deficit. And so that's finally the criterion. The criterion is very similar to, in spirit, is a flatness criterion, as I was saying, but there is a mesoscale, so that's the point. So you need a scale that is both very large with respect to the size of the hole, where you may have your topology, and sufficiently small with respect to the size of the mean curvature, okay? So the famous mesoscale. What do you want to know about this mesoscale? You want your surface to be flat in terms of your flatness control parameters. So we want that at scale S, the angular flatness is small, and we want that at scale S, the area deficit is between minus epsilon 0 and plus epsilon 0. Notice that I'm not asking this quantity to be non-negative. This is extremely important for the application. Okay, so if I have a flatness in this integral sense, then the conclusion is that M is going to be a sigma flat C1 graph with respect to H. To be honest, I may need to tilt a bit H, but let's forget about it for the purpose of an introduction. And notice that, and this is where this theory is really interesting, in my opinion, and really different from the usual theorems and flatness criteria we are used to work with. This flatness holds from the mesoscale S to a scale S star, which is both very small with respect to the mean curvature, inverse mean curvature, and nothing surprising here because it cannot be different than that. We already know this from the George and Allard, but you can propagate the graphicality also. There is an intrinsic bound, this R star. So R star will be how far above the mesoscale this area deficit stays larger than minus epsilon 0. Remember that the area deficit is decreasing in the range. So it could be very well be that at a certain point, this area deficit crosses the threshold minus epsilon 0 and become, say, even very negative, okay? So it's crucial here that the scale at which we infer graphicality, it's intrinsic to the surface itself through a control on the decay of this quantity, okay? So you may wonder, okay, but this theorem, it's, I don't know, too many conditions, I don't like it. So actually it's sharp. Okay, you may have suspected it is sharp because it completely solves the exterior isoperimetric problem and it creates this overlapping between the domain of resolutions of the various models. So that's, of course, I mean, quite create a strong suspicion that this thing is sharp. But actually it's sharp because for a generic surface with boundary mean curvature and a hole, flatness can only be established at a mesoscale. So this is actually true. At a mesoscale that is large with respect to the hole and very small with respect to the inverse mean curvature. Example, take an onduloid with constant mean curvature n and waist of size epsilon. So the onduloid, it's periodic, it will go on forever, but just take a period where it's a graph. Okay, then the onduloid is not flat with respect to the horizontal hyperplane, right? Because it's vertical here and it's vertical here. So is there a region where an onduloid of waist with waist of size epsilon is flat? There is. It's a region that, there is a region where if you express it as the graph of a function f, the size of this gradient is epsilon to the n minus 1 over n. And this actually it's a region of radii of order epsilon to the n minus 1 over n. So you see, there is a class of, there is a mesoscale here that is both very small with respect to the inverse mean curvature. Now mean curvature is n, so very small with respect to order 1. And very large with respect to the size of the hole. The onduloid has a non-trivial geometry at scale epsilon where it has the neck, okay? And that's exactly what you see. I mean, in general, so this is a very simple example of something with bounded mean curvature, topology inside the sufficiently small ball, family of, and flatness can only hold with respect to this plane at a scale that is both very large with respect to the size of the hole and very small with respect to the inverse mean curvature, okay? So in a sense, you see that the statement of this mesoscale criterion is optimal from this example, and I would say also from the fact that it completely solves the exterior isoperimetric problem. Okay, sorry I took a few more minutes, but I thought it was worth finishing it at a good point. Okay, thank you.
Thank you very much, Francesco, for the beautiful talk. Thank you. Any questions?
Sure, I have a question. So, to what extent do you think that these results could be extended to problems where there's not a monotonicity formula, like for anisotropic perimeter?
Okay, so for anisotropic perimeters, I am not even sure if the case lambda equals 0 of these things is known. That would correspond to exterior minimal surfaces. So minimal surfaces that have their condition in the complement of a compact set, right? So to be honest, yes, okay, you have Bernstein theorems, I guess, in sufficiently low dimension. I think these are there. And you would definitely need, so the proofs for exterior minimal surfaces, this kind of result is stated in some lecture notes of Leon Simon with a sketch of proof that is not exactly complete. And so, I mean, even the case of exterior minimal surfaces, in my opinion, in the literature wasn't completely, how to say, completely, well, not minimal, sorry, bounded mean curvature, was completely well described. But I mean, I think that in the case of anisotropic, even the exterior case is completely open. I would suspect, I think this is a completely general fact. So our proof uses monotonicity formula, uses our proof, it's in a sense, it's a careful modification of a paper of Allard and Almgren from the technical viewpoint, even if the results that we get are quite different in spirit, because there is this idea of allowing the deficit becoming negative and to look at the mesoscale conclusion. So I would say that it's more at the level of the proofs, but there shouldn't be a reason why this kind of statement qualitatively is not true in the anisotropic case. I would expect it to be true. Although, I mean, proving it's a different story probably. Will require definitely different ideas.
Thanks.
Thank you.
Can I ask? Hi, Francesco. Hi.
Hi, man.
Hi. Long time.
We're just seeing each other 2 days ago.
But now I finally understood what we were talking about. But
Okay.
I have a question though. So when W is the obstacle is convex, do you expect you showed lower bound and upper bound? I would expect the upper bound to maybe even always well, there's a harsh suspicion that maybe the the upper bound is always the correct one for at least when the obstacle is convex.
Yes.
About that?
Yeah, so I agree with you. It's very tempting. It's very tempting. However, I suspect that if it may not be actually the case. So because
the perpendicularity of the angles. Yeah, I know.
Yeah, so it should be close to. I think so. This is actually a problem I would like to understand better. So how these isoperimetric residues behave on convex sets. I think there is something very nice that you can say, because convex sets have all this structure, right? And now I think it's very cool, exciting, at least for people with my mindset, that you have a sort of natural free boundary problem, exterior free boundary problem on your convex set, right? That is this. And then understanding exactly how these minimal surface, they will want to be very flat. So if you start imposing some controls on the eccentricity of your set, right, you expect everything to converge somehow to the plane. And yes, I mean, I think it would be extremely interesting. I mean, because you got this family of exterior minimal surfaces with free boundary in your convex set, and then there is clearly a strong relation because convex sets are rigid between the geometry of the convex set and the properties of these minimal surfaces. So I think it would be fantastic to be able to say something. I think one can say something, but we haven't really tried yet, at least.
Yeah, I would even say that, it would actually be more interesting if the upper bound is not attained, because this would mean that for every direction, for every hyperplane that you put in your convex set, you have something which does probably better. Well, the residue is smaller than just projecting down the set onto this direction, right? So you could associate a parameter with respect to any direction, right? Which would be your RW when you force the nu to be that given direction.
Yes.
So for every direction, you get an interesting parameter that would actually be more interesting. Then you can study, how this thing behaves. Could be a suggestion to people like doing convexity. It's interesting.
Yeah, exactly. I agree with you, and it seems to be a rich direction that I don't think it has been started. I mean, it's very difficult when you talk about convex sets saying it has not been done. These are not, but these may have not been done. Probably.
And one little question again. So about just the classical local flatness criterion that you mentioned. So the point is that you wanted to mention monotonicity there, because I think like the very first thing you showed on one of your first slides was that when so lambda is the upper bound on the mean curvature, that scales like 1 over length, right? So when you're at a scale which is smaller than 1 over lambda, then you want, exactly. Oh, this exactly. So you wanted okay. So I see. So the point is that it's a graph on this region of scale rho, right? But in principle, when you take lambda higher and higher, right, then this condition becomes weaker, right? So that was a bit confusing, but I guess the point is that the conclusion would also be weaker because you're only a graph at the scale rho. And since you have monotonicity, then I guess you only care about this, almost being flat when rho is super small anyway. So
yes, and there is no universal rule that you can. I mean, the example I was making, right? If you think about catenoids, so in this case lambda is 0, and then you can just scale these so that but I mean, that's actually one of the in a sense revolutionary aspects of this kind of theorems when the Georgi Fist proved it in the 1960s. I mean, the idea that you get conditional regularity, right? That there is a scale invariant quantity with smallness actually then trivializes the geometry of your object. I mean, this, I think it's in a sense, it's not, nowadays it's something that we give for granted, I would say. But I think this is a very deep aspect of these theorems. I mean, with respect to.
Great, thank you.
Yeah, thank you.
So if no more questions, thank you very much, Francesco, again.
Okay, thanks again for the opportunity to present this work. Bye, everybody.
See you, Francesco.